Okay, let's go ahead and get started. So thank you everybody for taking some time out of your day to come and listen to some updates about Green Bank Observatory and as well as some great science about the telescope and what we've been doing. So today, as usual, I'll give a brief update on Green Bank Observatory and just what's been going on around the site. And then what will be followed by a fantastic science presentation about some bistatic radar observation done with Goldstone and the GBT. So on the GBT side of things, how are we doing? COVID cases continue to drop around the state, which is mimicking again what's going on within the United States. So right now we're around 1% of all tests are positive for COVID-19, which is fantastic news. The number of vaccinated people in the state is also on the increase, although that's going much more slowly. Up to about 47% of the population is vaccinated, or about 54% of the eligible population, that is the people ages 12 and older are vaccinated, which is good news. Across the county, we still seem to catch the occasional case here and there, but overall the total number of cases is staying very low. On site, we're all getting back into work. I'm actually sitting in my office right now for the first time in a long time giving this talk, which is great news. The majority of our staff here at Green Bank Observatory are vaccinated. All of our staff are now welcome to come into work. And we are still doing health checks, of course, to just make sure everybody is healthy. But we anticipate a full return to operations on site on September the 1st. At that point, everybody will be in their office. We'll be in and we'll actually get to start seeing each other over lunch and things like that. So it's very exciting to see within our area just the vaccines and the drop in the COVID cases coming through. On site, of course, the GBT is typically in a 24-hour day, 7 days a week operation. Of course, this is summertime, which means we're doing a lot of maintenance. So we're painting the telescope. We're doing a lot of repairs to actuators, to the track and things like that, as we do every summer. This is also the year of our triannual inspection. So every 3 years, we bring in an outside company to do a full inspection of the GBT to just make sure that structurally the telescope is sound. So that process is ongoing right now as well. And so that's good news. We like to get inspected so we can make sure we have a good telescope to last for a long time into the future. Our other really exciting news since the last one of these community talks is that our Science Center has reopened. That means that people can actually go inside the Science Center for the first time since March 13th of last year. Of course, everybody has to be masked to keep everybody safe, but still it's really been great to see the tourists starting to come back in again. Our bus tours have restarted. Now we're able to have people in the exhibit hall and to give lectures and so forth. So we're very happy to be back into fully sharing the fantastic science that we do here on site. One of the things we started in the pandemic are these walking tours, and they are continuing actually. We're having one walking tour a day for those folks that would rather go out and walk the distance down to the telescope, spend a little bit more time with our tour guides, get a chance to stretch their legs. But as I said, we also have the bus tours going on at the same time. Other big news at the observatory is the call for proposals for the 22A semester is now out. So this is the semester that runs from February 1st. It begins on February 1st of 2022. Those proposals are due at the beginning of August. The actual deadline is on at 2100 UTC on August 2nd. The full details of the call for proposal are online. You can just go to greenbankobservatory.org and you'll see up in our slider at the top of the screen, you'll see the call for proposals. You can click on that. If you're really into getting into the details, you can also go into the, click down into our science menu and go to GBT observers and you can get the proposal call there. Follow this link. If you're interested in putting a proposal in and you don't know the GBT very well, I encourage you to take a look at our proposer's guide. That's also online under science and then under GBT observers and proposals. And that'll teach you a lot about the types of things that GBT can do and all the fantastic ways you can use our telescope in order to move your science forward. So again, call for proposals is out. Submission deadline is on August the 2nd. So the last thing to mention are just upcoming events. Of course, our community Zooms continue. Our next community Zoom will be on July 21st. And that'll be Jaime Pineda talking about the ion neutral connection in dense cores. And then our single dish school signup is also now open. Again, you can just get there through the main web page, go down to GBT observers and you can see the single dish training workshop. This is a 5-day long school that teaches more than just how to use a telescope. It teaches you the basics of radio astronomy, It's intended for people who already know astronomy, know physics, and they just want to learn about radio telescopes and how they work. At the end of that single day school is an observer training workshop for the GBT. So you could sign up for both, or just the observer training workshop, or just a single day school. We're also very happy to say that the single day school will be jointly done this year with Arecibo Observatory. Arecibo staff will be giving some of the lectures at the school, and we're also working with them to come up with a way to do some archival data reduction from some of the great data that came from Arecibo telescope. Finally, I should mention the school will be hybrid. So if you are fully vaccinated with one of the 3 recognized vaccines from the FDA, you would be very welcome to come in person, but we are also going to offer remote options for those who, for various reasons, travel would be too difficult. So we'll be running this with about half the intent is about half the people will be in person and half remote. When you go to sign up, it'll ask you what you think you're going to do. This isn't obligatory to say if you say remote, you must be remote, but it's more to give us a feel for the breakdown of the workshop and the participants in the workshop. So I encourage you, if you want to learn more about radio astronomy or want to learn more about the GBT in particular, to please sign up for the single day school. So with that, I'll just thank you again for your time here and for taking time out of the day. And I will hand this off to Jay Lockman to introduce today's speaker. So thank you.
Thanks, Karen. Our science speaker today is Marina Brozovic from JPL, who's going to be speaking to us about bistatic radar observations with Goldstone and the Green Bank telescope. And let me just remind you, if you have any questions, to use the Q&A button at your lower right, and we will take those at the end of the presentation. Go ahead, Marina.
Okay, well, good morning. Really nice to be here. I hope you can see my screen well. Okay, so without further ado, I'm going to introduce you to our current radar capabilities at Goldstone. These are our 2 antennas, DSS-14 and DSS-13. DSS-14 is 70-meter diameter dish, and it has a very powerful transmitter, almost half a megawatt of power. It works in X-band, and it's fully steerable. It pretty much covers everything north of declination -35. Then we also have our smaller antenna, DSS-13, that dish at the bottom. It's 34-meter dish. It has 80 kilowatt transmitter, and it works in C-band. Now, DSS-14 is much more powerful, but DSS-13 has the highest imaging resolution capability. We can resolve objects down to 2-meter resolution per pixel, 2 meter per pixel, and DSS-14 can go down to 4 meters per pixel. However, DSS-14 is kind of self-sufficient antenna. It has both transmitter and receiver, and that's how we most time use it. We use it by itself. And DSS-13 only has a transmitter. So that means we need to receive with some other antenna. And we did it with both Arecibo and Green Bank in the past. And obviously, Green Bank is always a great addition because it's a phenomenal, it's a 100-meter dish, and it greatly boosts our signal to noise. And indeed, if we use it with DSS-14 and receive at Green Bank, we boost our signal to noise by more than a factor of 2. And I want to point out that after Arecibo, DSS-14 working with Green Bank, it is the world's most powerful radar configuration. And yet, I have to say, we are still about a factor of 7 less sensitive than what Arecibo was by itself. So how does radar work? Well, radar stands for radio detection and ranging, and it's very much like a flashlight. So you are transmitting microwaves, and they're bouncing off from nearby objects. And not only the echo that comes back is holding information about very precise measurements about its line of sight, position, and velocity, but it also carries imprints about objects' rotation, about how large it is, about its surface details, and radar scattering properties. And with radar, you control what type of signal you're transmitting, and you can get different types of data back. So at the kind of very basic, you're just transmitting a plain sinusoid wave of a fixed frequency. And if this as this is bouncing off from a rotating asteroid, it's being dispersed in Doppler frequency. And this is kind of the most basic detection by radar. You just get this bump in echo power spectrum in Doppler frequency. And the width of the bump, it's telling you something about the size of asteroid, about how fast it's rotating, and how its spin axis is aligned with respect to radar. So this is how all our radar observations start, just what we call CW experiments. And only when we had that, we move on to ranging. So now we are trying to detect, to get that one ping off an object and get a very precise measurement in line of sight distance. And we use that for orbit determination. Right there during the track, we improve the orbits of asteroids. And only when that is done, then we see, well, how much signal do we have? Do we have a budget of our signal to noise that we can divvy it up in pixels, how many pixels in Doppler frequency and in range, so we can reveal how an object looks like. And that's when we do imaging. So this is this very last image when we really reveal how an object looks like, sometimes with tens of thousands of pixels, and we can see great amount of detail on the surface. So you know, all this sounds pretty good, but that's kind of what's the catch. Well, radar, the signal drops with a fourth power of distance. So something that is twice as far is going to have 16 times smaller signal to noise ratio. So most of the time what we observe, we are observing objects that are within, say, 1/10 of an astronomical unit, and they're a few hundred meters in size. Obviously, if they're larger, we can detect them farther away, and if they are smaller, they have to come in closer. And I'll be showing you, obviously, I already started showing you radar images, and that is very different than your plane of sky image. So on the right side of the screen, you're seeing plane of sky models. This is how you would see it through your telescope. And then on the left side of the screen, you're seeing how radar, these are radar delayed Doppler images. They're very different. So always keep in mind that radar beam is coming, the way we orient them, it's coming from the top of each frame. So it's illuminating the object. And while in plane of sky images, both your X and Y, so horizontal and vertical dimension, they're spatial dimensions. But in the case of radar images, the vertical dimension is the only one that's spatial dimension, but it's not X and Y, it's not plane of sky. It is Z, it is distance, it's a depth, it's a distance from the radar. You're building a picture of the object as a function of distance from the radar. And then on your horizontal axis, this is not spatial dimension, this is Doppler frequency, which is just a measure of how fast parts of the asteroid are coming towards you or moving away from you. So they're a little bit non-intuitive, but we have software that does inversion of radar images into three-dimensional shapes and speeds. And radar history, radar observation history starts in 1968 with the detection of asteroid Icarus at Goldstone. And we've been very busy ever since. You see this black curve, that's a cumulative number of detections going up and up and up. And in the past 20 years, it's been very busy. And I'm just showing here the list of all the objects in 2021 that we observed with Goldstone. Unfortunately, our SIBO is no longer here. And currently in our database, we have close to 1,000 near-Earth asteroids observed. Not all of them, some of them just have that basic detection, you know, that bump in a echo power spectrum, but some of them also have images. At the record for our SIBO in 2019 ended up detecting 125 objects. And Goldstone, because we are 15 times, so our DSS-14 is 15 times less sensitive than what our SIBO was. We observed 39 objects in 2015. And Greenbank was used as the receiver antenna for 30 near-Earth asteroids and 1 comet. And the first collaboration was in 2001 between Arecibo and Green Bank. And the observations were actually led by Jean-Luc Margot, now at UCLA. He gave a really nice talk a couple of weeks ago at the Green Bank webinar. And then in 2002, there was a collaboration between Goldstone and Green Bank. This was led by Lance Banner. He's the PI of radar program here at JPL. So let's start with some of the really good imaging targets we had in the past between Goldstone and Green Bank. This is a binary gas story, 2004 BL86. So binaries are, so what I mean by binary, you have a primary object and you have a companion, you have a small satellite that's orbiting around it. They're relatively common in the near-Earth population. So among the near-Earth asteroids larger than 200 meters, it is estimated that at least 15% are these binary objects. This one approached relatively closely. It's in 2015, it approached at 3 lunar distances, and it was quite large. The primary, something like 300 meters in size, the satellite, about 70 meters. The satellite was first noticed, there was a hint of it in the light curves. But then once when we pointed our beam and imaged it, it was very clear that this is a binary system. So here's again, there's this animation of delayed Doppler images. On the vertical axis, this is your distance from the radar. It's a spatial dimension. And if you want to compare how large objects are, well, you just count the number of pixels vertically. And this is the primary, you see about half of it. This is a proxy for its radii. And then you see the satellite. And then on a horizontal axis, this is Doppler frequency. So the reason why primary is so much wider, appears larger, is because it's spinning much more rapidly. So it's spinning with like 2-hour period, and the satellite is narrow in Doppler frequency because it's rotating very slowly, like 15, 16 hours or so. And this is what we imaged with 3.75 meter resolution. You see great amount of detail on the surface of the primary. You're seeing these kind of lumps and these bright specks. These bright specks, based on my past experience, they're most consistent with the surface boulders. So you are perhaps looking at something, meter-sized boulders on the surface of an asteroid. It would not be unusual, given if you have seen images of Bennu and Ryugu, and Itokawa for that matter. So obviously, 3.75 meter resolution, it can reveal an object that's 200 meters in size in thousands of pixels. And this is how we think that most of these binary objects in near population look like. There is a primary top-shaped that is kind of bulging at the equator, because that is what happens when you spin up a rubble pile. It's usually they're rapidly spinning 2 to 3 hours. And then they have this much smaller satellite that is orbiting it. And one of the reasons why we are always kind of excited when we discover a binary is because from Kepler's third law, we can estimate the mass of the system. And if we image it with radar, we know exactly their sizes, so we can calculate the volume and we can get the density out. If you know the density, you know what's inside of an asteroid. And that's not easy to find out with other methods. So we are learning something about what's inside. And their densities usually come around 2 grams centimeter cubed, even or smaller, which means there's a lot of empty space. So in fact, they're really great insight about structure of asteroid. They are showing us that these are rubble piles, loosely held together by gravity. Okay, and this was another good targets in 2015 we observed, and this one comes really with a good story. So it's called 2015 TB145, and that is not the greatest name, but there is a way to decipher it. So this one was discovered. It was our target of opportunity. It was discovered 3 weeks before its closest approach. This was with Pan-STARRS telescope on Hawaii. And it happened to make the close approach at only 1.3 lunar distances, exactly on Halloween. So Obviously, this was immediately getting picked up in the media. It was a large object, so it was kind of building, you know, you have suddenly arriving big thing at your doorstep, perfect for Halloween. Then another thing we noticed is that its orbit was consistent with the Jupiter family comet, but it wasn't showing any cometary activity. And we've seen objects like this before, and we usually speculate that they are perhaps dead comets. You know, something that went around the sun one too many times, lost its old volatiles, and you're looking at the dead comet. So even better for Halloween. And then our SIBO started imaging first. And you see this image, this is to your left. And if you're pretending this is not a radar image, you're looking at plano sky image, this looked like a skull. I mean, there's like you definitely have a skull, 2 eyes, nose, and a teeth. And media obviously had a field day. You can't write this stuff up. I mean, you can't make it up. Then DSS-14 and Greenbank started imaging it a little bit later. Obviously, it was in different orientation. Amazing looking object with a lot of these dark, radar dark features, which are probably, you know, could be impact craters, large concavities. There's evidence of these surface ridges. And another thing with Goldstone, this is, you can directly compare. This is 3.75 meter resolution in range to your right, and 7.5 meter resolution to the left with our SIBO. That was the limiting resolution for our SIBO, 7.5 meters. We could go, with DSS-14, we're going twice as that. So we can also, you know, we can see more detail. But not always do we image large objects. Sometimes we image small ones too. And this is a story about 2012 TC4. Small object. It first made a close approach in 2012 when it was discovered shortly before that. It's only about 20 meters in size. Pan-STARRS discovered it. It approached at quarter lunar distance. Both our SIBO and Goldstone had troubles at the time, so we did not get to observe it. It was observed only with optical telescopes, and then it was pretty much, you know, not lost, and it was rediscovered a month before its close approach in 2017. It approached even closer. It approached at only less than 8 Earth radii. And this is the time when we ended up imaging it with our smaller antenna, DSS-13, and Greenbank. And this Greenbank was absolutely vital in this case, because not only does it have large surface area, but it also, with a single antenna, we can switch fast enough between transmit and receive cycles when a target is within 2 lunar distances. There is this optical switch, just can't do it fast enough. So you need to continuously transmit from one antenna and receive on another antenna. And we used DSS-13 because, you know, we had signal to burn. It was that close. And we needed 1.75 meters, 1.9 meter resolution imaging, because when you have an object that is really small, we revealed in these sequence of images, it was only 10 by 20 meters. Every pixel counts. And so DSS-13 was perfect for that, because it revealed a shape of this small object, about, as I said, 10 by 20 meters, elongated. We followed it for many hours, and it has a very short rotation period, well less than an hour, about 0.2 hours. This was very first demonstration that this high resolution imaging system works. There are predictions theoretical that this asteroid changed spin state, because when you have something approaching this closely, then due to tidal interactions, the spin state before and after ends up being different. So this is something definitely that we are going to look into in our radar data. And this is my last object that I want to show you. This is probably my favorite to date. This is 2003 SD220. And it is a contact binary. So that is, it has this kind of, resembles a bowling pin or a peanut. And this is another relatively common shape in a near-Earth population. We know that in this population that is larger than 200 meters, and about at least 15% of objects look like this. They have this bimodal mass distribution. And so this one just happens to be also easily accessible. So it is on NASA's NHATS list of potential human accessible targets. That means it's relatively, you don't need much fuel to get there and back. You can make a short mission. It is making 5 close approaches within 10-year period. And the closest was in 2018. It approached at 7 lunar distances. And when we imaged it, this is a sequence of 3 images that we obtained with DSS-14 was transmitting, Green Bank was receiving. This is 3.75 meter resolution. And the long axis of this object is about 1.5 kilometers. It's a very large object. And it's very elongated. Rotation period, super slow, 12 days. And this is another reason when we end up really needing Green Bank, it is when the rotation period is so slow that the Doppler bandwidth of the object is very narrow, and we just can't resolve it if we do experiments on the single antenna. But if we receive on the second antenna, then we can put as many pixels as we need in Doppler frequency to resolve its shape. So great amount of detail visible in the feature on the surface. These radar bright specks you see, again, this is most consistent with a maybe 10 meter size boulders or perhaps smaller. And this is the most interesting on December 17th. This was really interesting orientation. It looks like kind of a loaf of French bread. And it has these very interesting kind of ridges and kind of scalloped feature. So I really can't wait to see a shape model that is going to come out of this. Ed Rivera Valentin from LPI, he's working on this. And we are going to have another chance to observe it this December. It's arriving at 14 lunar distances, so a little bit further away, but because it's such a slow rotator, we're expecting images that are going to be of exactly the same quality. So with this, I'm going to close. And yeah, we're looking forward to working with Green Bank again. Thank you.
Thank you very much for an excellent presentation. These were some really fascinating images of fascinating objects. We have some questions. And the first is, why is BL86 nearly spherical?
Well, BL86 looks pretty much like this. So if you can see my screen, this is, we didn't do reconstruction. It's in a progress. I believe Patrick Taylor from LPI is working on that. But it is basically, it's probably top shape. It probably looks exactly like this. So it's not spherical. It's when you spin up something that is a pile of rocks of various sizes, and that is loosely held together by gravity, it is going to bulge at the equator. So it has just kind of, you know, this equatorial ridge and sloped hemispheres. So it's symmetric, but it's really not spherical. We rarely see from the asteroids we actually have the shape model reconstruction. We haven't seen that many spherical ones. They usually have some kind of features.
And that leads right into the next question. Have you seen any rocks as asymmetric as Muamua, i.e. 10-to-1? Okay,
so I believe that aspect ratio for Muamua has been revised since. I believe that it's, I think last thing I heard was 6-to-1, which is extraordinary, which is still absolutely exceptional. Well, speaking of extremely elongated ones, we just observed one. It was 2003 WD-158. That one has extreme elongation ratio, perhaps definitely larger, 1 to 2.5, maybe 1 to 3. But no, we have never seen anything at the level of Oumuamua. That was a very unique object.
Okay, another question. Did any of the Arecibo radar transmitter equipment survive the collapse? And if so, could it be repurposed for use in either the GBT or Goldstone?
Unfortunately, I don't think that anything survived in that crash because yeah, the transmitter, everything was up there, and once when it crashed, I don't think so. I don't think it's possible that anything survived. But somebody from Arecibo perhaps knows the answer better.
And a question about whether a significant increase in radar frequency would be able to give better resolution of targets.
Yes, of course. You know, you have there is actually a facility like that, like Haystack. There is a Haystack radar in Massachusetts. It's usually, I believe, it's used for space debris. That one has capability of few centimeter imaging. But obviously, you know, it's a trade-off. You know, the transmitter is not that powerful, so it can only image objects that come much closer. I believe it was used on one asteroid, 2012 DA14. I don't think it was used since. So potentially you already have radars, smaller facilities that can do higher resolution imaging, but it needs to be kind of demonstrated on a kind of regular basis.
Now, here's a question about the duality of many of these asteroids. Is the satellite attracted by the primary as it travels, or does the satellite break off the primary?
So yeah, so that is one of the kind of insights that you know, we take these shapes for granted. That the binary systems look like this, but it was really radar, the first reconstruction of this 1999 KW6 that we first time really noticed how these objects look like, and that ended up spinning a whole bunch of theoretical work on it. And so the theories that came out of it was that when you have rapidly spinning primary, that the material on the equator is so loosely bound that it's actually starting to float off and can form a satellite. So that is kind of the shape of the primary is directly related to the origin of a satellite. It's basically transfer of material into orbit. And then there is another also potential theory, and that is that it fissions due to rapid rotation, that the rubble pile just fissions and you end up with a satellite.
Yeah, if I may just ask for an elaboration on that, how close to the Earth could something like this come before it was tidally disrupted?
Yeah, the tidal disruption, it has to come really close. It has to come within 2 Earth radii. So their models on, you know, there's also kind of interest in how contact binary, how the peanut shapes come to be. You know, what is their origin? Maybe close planetary flyby ends up pulling apart. It has to come, with respect to Earth, it has to come fairly close. Yeah, it's I believe it's something like less than 2 Earth radii.
We have a couple of comments from Arecibo that no usable equipment was left after falling several hundred feet. And then 2 more questions here. Could collaboration with the SKA allow a further distance material at a further distance to be detected?
Well, it is, well, we'd have to look first of all in longitude coverage. It's not just, you know, and also I'm not completely familiar what would be the size of the dish. So I would have to look into numbers to answer that question properly.
Okay, and a final question. Suppose a certain large radio telescope installed a high frequency radar. What is the highest frequency that Goldstone telescopes could be used as receivers?
Yes, so we obviously have we have X-band receiver, we have S-band receiver. We don't have, for example, when we are transmitting with DSS 13, we can't receive, we don't have C-band receiver. So currently it's X and S. I am not aware of other frequencies.
But I believe the Goldstone surface is accurate enough to support receivers higher than X-band.
Yes, 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 correct.
And oh, I have there's a comment coming in. Ka band is the highest receiver at GDSCC. I'm not sure what GDSCC is.
It's a solar system radar. It's DSS 14.
Ah, okay, okay.
It's
So
exactly. Thank you. I'm guessing that was probably Lance online.
yeah, I think it's someone with inside information. That's certainly true. Okay, one final question. You mentioned imaging a possible dead comet object. Have you used this method on a live comet? And if so, how does the trail emission affect your ability to get a read on surface shape?
Oh yes, of course. Yeah, we have in our data set, I believe that we have about, our SIBO image most of these comets. I think it was about 20 comets in radar data set. So you have to understand, you know, comets, unfortunately, they don't come close enough to image them that often. But there are some extraordinary images of comets out there. And not only, yes, you can image with delayed Doppler imaging how a nucleus look like, but also if you do the CW, if you do that just basic, that Doppler frequency echo power spectrum, then you can actually see the tail from the you know, comet debris. So you can actually detect the I'm forgetting now the word, the basically about the small particles surrounding the comet, and there have been Anne Berkey from our SIBO, she wrote a really nice paper on that. So yes, absolutely, we can detect the nuclei, the coma, and the tail, and particles that are making up the coma.
Thank you very much. And thanks to everyone who attended and asked questions about this wonderful, interesting topic. And thank you again, Dr. Brozovic, for your presentation.
Okay.
Please join us again in 2 weeks when we will have Jaime Pineda talking about dense cores in star-forming molecular clouds. Thanks very much, and goodbye.